Right now, light is crossing the room where you're lying. It is moving at 186,282 miles every second, which works out to about 670.6 million miles an hour. The sunlight resting on your wall left the surface of the sun 8 minutes and 20 seconds ago after crossing 93 million miles of empty space to reach you. If the sun were to vanish this very instant, you would keep seeing it shine for more than 8 more minutes, warm and steady and ordinary, with no way at all to know that anything had gone wrong. Nothing you could do in that time, no message, no glance, no instrument, would tell you the truth any sooner. Most people carry this number in their heads as a fact about light. It is the thing photons do, the speed a beam travels, a headline figure you learned once and filed away. Fast. Yes, faster than anything else, but still just a property of a particular kind of stuff. Light moves quickly, the thinking goes, the way sound moves through air or ripples move across a pond, and this happens to be the top speed for that one substance. That picture is comforting, and it is almost entirely wrong. Physicists have a stranger and far more accurate way of describing this limit. They will tell you it is not really the speed of light at all. It is the speed of causality, the absolute maximum rate at which any cause anywhere in the universe can produce any effect. Light just happens to be the fastest thing that obeys the rule. The rule itself was never about light. It is stitched into the geometry of space and time, and it governs everything: the fall of a stone, the pull of gravity, the flick of a thought crossing a nerve. Before we go further into that idea, one small thing. If these slow walks through the physics of the universe help you drift off, a like or a subscribe genuinely helps this channel survive, and you can find these same episodes on Spotify for the nights you would rather only listen. That is all. Now settle back and let us keep going. Here is the first strange consequence, and it is worth sitting with. Because the limit is finite, and because signals take time to arrive, you are never actually experiencing the universe as it is. You are experiencing it as it was. The moon you see hangs where it stood about 1.28 seconds ago, because that is how long its light takes to cross the 238,000 miles between you. The sun, as we said, is more than 8 minutes stale. The nearest star beyond it, Proxima Centauri, shows you light that left it more than 4 years ago. Look at a galaxy on a clear night and you are staring at a photograph the universe developed millions of years before you were born. So the sky is not a scene. It is a stack of delays, each object reaching you from its own moment in the past, and the farther out you look, the deeper into history you fall. There is no single now that you can point a telescope at. The word now, spread across the cosmos, quietly loses its meaning. This is where physicists reach for a particular shape to make the idea hold still. They call it a light cone, and it belongs to every single event, including this one, the moment you are living right now. Picture it like this. Imagine space-time as an infinite black lake, perfectly smooth, stretching in every direction. Every event that ever happens drops a stone into that lake. The ripple spreads outward, and its out edge travels at exactly the speed of the limit, no faster. That expanding edge is the boundary of everywhere that this moment can ever reach. Anything inside the ripple can be touched by what you do now. Anything outside it cannot, not ever, no matter what you try. And there is a second cone, reaching the other way, into the past. It gathers up everywhere that could have already sent a ripple to you, everywhere whose light and influence has had time to arrive. Together those two cones, one opening into your future, one narrowing back into your past, mark the full extent of your causal reach. Everything you can affect lies in one. Everything that can affect you lies in the other. Now hold that picture and let it grow cold, because here is the part that unsettles people. Most of the visible universe at this instant sits completely outside your light cone. You can see it, its old light having crossed the gap over billions of years, but you cannot touch it. You cannot signal it. You cannot change one atom of it, and it cannot change you. Not now. Not in 1,000 years. Not through any means that physics allows. The stars are not merely far. Most of them are sealed away, on the far side of a wall built out of time itself. That can feel like a cruelty, as if the universe handed you a window and then bolted it shut. But the very same wall that seals you off is the thing that keeps reality from falling apart. To see why, you have to ask a question that sounds almost childish and turns out to be one of the deepest in all of physics. Why should there be a speed limit on cause and effect at all? Why not let one thing touch another instantly, everywhere at once, with no delay and no ceiling? The answer is that a universe with no such limit would tear its own logic to pieces. It would lose the order of before and after. It would let effects arrive ahead of the causes that made them. To understand that, you need one fact that took physicists a long time and a great deal of pain to accept. In our universe, there is no single, universal clock ticking the same for everyone. How much time passes between two events, and even which of two events counts as first, can depend on how fast you're moving. Two observers, gliding past each other, can honestly disagree about the timing of things, and neither of them is mistaken. This is not a trick of bad measurement. It is how space-time is actually built. The name for that deep structure is Lorentz invariance, and every equation of relativity rests on it like a house rests on its footings. Now bring the two ideas together. Because different observers slice up time differently, the finite speed limit is the one thing that keeps everyone agreeing on what caused what. Stay under the limit, and every observer, however they are moving, will always see the cause happen before the effect. The strike lands before the bruise blooms. The word is spoken before it is heard. The order holds for everyone, always. But let a single signal break the limit, even once, even by a hair, and that guarantee shatters. The mathematics is not shy about it. If any influence travels faster than the ceiling, then there exist perfectly valid frames of reference, ordinary observers moving at ordinary speeds, who would see that signal arrive before it was ever sent. The effect would come first. The cause would follow, trailing behind its own result like a shadow that fell an hour before the object that cast it. Sit with how ruinous that is. Send a faster-than-light message to a friend, and in someone's equally legitimate view of the same events, your friend receives the message before you decide to write it. They could answer before you asked. You could learn the outcome of a choice you have not yet made, and then make the opposite one. The whole chain of because and therefore, the thread that ties every moment to the next, would come loose. Past and future would stop being different kinds of thing. They would just be directions, and you could stroll between them, unmaking as you went. The universe, as far as anyone can tell, does not allow this, and it does not allow it not because of some patrol force watching the boundary, but because the boundary is woven into the fabric that time and space are cut from. The speed limit is not a fence somebody built across an open field, it is the shape of the field. Ask why nothing outruns it, and the honest answer is that outrunning it would mean stepping outside the geometry that lets there be a before and an after in the first place. This is why it matters so much that light, of all things, travels at exactly this speed and no faster. Light is not special because it is bright, or because it warms your face, or because you happen to see by it. Light is special because it carries no mass, and a massless thing rides the ceiling for free. It moves at the maximum rate the structure of space-time permits, which is precisely why we noticed the limit through light first, and then spent a long time confusing the messenger for the message. The number belongs to space-time. Light merely spends it fully, holding nothing back. Everything else, everything with even the faintest whisper of mass, runs into a different wall long before it ever reached that edge. A proton, a spaceship, a single grain of dust, your own body lying still in the dark, all of these are barred from the ceiling by a cost that climbs without end as they try to approach it. But that is a story for a little later, a wall of its own, made not of geometry but of energy piling up toward infinity. For now, hold on to the reframing, because it changes the whole shape of the question. You began the night thinking of a fast thing, a beam, a photon, a top speed for a certain kind of stuff. What you are actually looking at is the tempo of existence itself. It is the rate at which one event is permitted to reach out and matter to another. It is the reason the sky is a museum of the past. It is the reason distant galaxies are visible and untouchable at the same time. It is the reason your today has a yesterday behind it, and a tomorrow ahead, cleanly separated, never allowed to trade places. There is a stillness to that once the strangeness settles. Deep space is silent in a way we rarely imagine, because silence needs a medium, and the vacuum has none. No sound crosses it. No signal outraces the light. There is only that quiet, patient crossing, a beam of light drifting across empty distance for years, for centuries, for millions of years, carrying the news of some far event toward whoever waits at the other end. The universe does not hurry, because it cannot. It moves at one fixed pace, and that pace is the same for a supernova and for the photons leaving the lamp beside your bed. And here is the thought to rest on before we turn back to the human end of the story. For all its grandeur, this limit is not an abstraction happening somewhere far away. It is running right through you, this second. Every nerve that fires, every signal crossing your body, every ordinary cause producing its ordinary effect, all of it obeys the same ceiling that binds the galaxies. You are not watching the rule from outside, you are made of it. The pace of cause and effect is the pace of you. Which leaves us with a puzzle that is almost embarrassing in its simplicity. We have been speaking of this number, 186,282 miles a second, as though it were obvious, as though anyone could have reached out and read it off the sky. It is nothing of the kind. For most of human history, no one even knew that light took any time to travel at all. It seemed instantaneous. Strike a flame in a dark room and the far wall lights the same instant, or so it appears, because the delay is far too small for any eye to catch. To learn that light had a speed, and then to pin that speed down to the last digit, took brilliant, stubborn people, centuries of failed attempts, and a few beautiful accidents. For most of human history, light seemed to arrive the instant it left. You strike a match, and the room is bright at once. You open a shutter, and the field outside is already there. Nothing about ordinary life suggests a delay. Light felt less like a traveller and more like a fact, present everywhere at the same moment. The first crack in that idea came from a moon you have probably never seen with your own eyes. In the 1670s, a Danish astronomer named Outrun was watching Jupiter. Not the planet itself, but one of its moons, a small bright world called Io. Io circles Jupiter quickly, once every 42 hours or so. On each lap it slips behind the giant planet and vanishes into shadow. From Earth, that looks like a tiny lamp winking out, then flaring back on again. Astronomers had been timing those eclipses for years. They made a natural clock, a steady heartbeat far out in the dark, ticking against the void. Roma noticed something the clock was not supposed to do. The eclipses did not keep perfect time. When Earth was on the near side of its orbit closest to Jupiter, Io reappeared right on schedule. But months later, when Earth had swung around to the far side of the Sun, the same eclipses ran late. Not by a little, by minutes. The moon seemed to be falling behind, then catching up again, in a slow yearly rhythm that tracked the changing distance between the two planets. Here is where the detective work begins. A lesser mind might have blamed the moon. Maybe Io wobbled. Maybe its orbit breathed in and out. Maybe Jupiter's grip was somehow uneven. Roma looked at the same pattern and saw something simpler and far stranger. The moon was not misbehaving at all. Io kept perfect time. What changed was the distance the news had to cross to reach his eye. Think about what an eclipse really is. It is not an event you touch. It is an event you see. The light that carries the picture of Io sliding into shadow has to travel all the way from Jupiter to Earth before you know anything has happened. When Earth sits close to Jupiter, that light has a shorter road. When Earth sits far away, on the opposite side of the Sun, the light must cross the entire extra width of Earth's orbit before it arrives. If light takes time, then the far eclipses should look late, and they did, exactly as much as they should. That was the leap. The delay was not the moon running slow, it was the light running late. An effect could lag behind its cause by minutes, simply because the messenger had farther to travel. Römer worked out that light needed something like 22 minutes to cross the full diameter of Earth's orbit. His number was rough, and the true size of that orbit was barely known at the time, but the idea underneath it was solid, and it was revolutionary. Light was not instant. Light took time. For the first time, a human being had caught it in the act of being late. Not everyone believed him. The delay was subtle, the timings were difficult, and the notion that light crawled rather than leaped offended plain common sense. The confirmation came from a different direction about 50 years later, from an Englishman staring almost straight up. In 1728, James Bradley was trying to measure the distance to the stars. He was hunting for a tiny shift in a star's position as Earth moved from one side of its orbit to the other. He found a shift, but not the one he was looking for. The stars seemed to trace small circles over the course of a year, all tilted the same way, as if the whole sky leaned gently into the direction Earth was travelling. The explanation is beautifully simple, and you have felt a version of it yourself. Walk through rain that falls straight down, and you have to tip your umbrella forward, because your own motion makes the drops seem to come at a slant. Bradley realised starlight does the same thing. Earth races along its orbit at enormous speed. To catch a beam of starlight coming from almost overhead, you have to tip the telescope forward by a hair into the direction of travel. The faster you move compared to the light, the larger the tilt. That small tilt was measurable, and it hid a number inside it. Bradley knew roughly how fast Earth moved along its orbit. He measured the angle by which the stars appeared to lean. From those two facts, pure geometry handed him the speed of the light itself. No spinning wheels, no distant mirrors, no laboratory at all. Just a telescope, the steady motion of the Earth, and a triangle. His answer was about 301,000 kilometers per second, which comes out to roughly 187,000 miles per second. Sit with that for a moment. The modern value, pinned down with atomic clocks and lasers, is 186,882 miles per second. Bradley, in 1728, with a telescope and a carefully measured angle, landed within a fraction of a percent of the truth. He was startlingly, almost eerily close, and he got there with mathematics you could sketch on a single page. Between them, Römer and Bradley did something quieter than they knew. They were the first humans to prove that news itself travels at a finite pace. Every event in the universe sends out its report at that same limited speed, and never any faster. The eclipse of Io that Römer timed had already happened when its light reached him. He was watching the past. The starlight Bradley tipped his telescope to catch had left its star years, sometimes centuries, before it grazed his lens. That is the strange gift buried in their work. The sky is not a picture of now, it is a picture of then. When you look up, you're not seeing the stars as they are. You're seeing where they were and how they shone when their light first set out toward you. Some of those stars may no longer exist at all. Their light is still arriving, faithful and slow, a message sent from a source that may already be gone. Picture Io one last time, a small bright lamp set beside a giant planet blinking out behind it and flaring back on a schedule you could set a clock by. Now imagine watching that lamp across a field that slowly widens through the year. When the field is narrow, the light of each blink reaches you almost at once. When the field stretches wide, the same blink takes longer to cross it, and the lamp seems to fall behind. Nothing about the lamp has changed, only the distance the light must walk to find you. That was the discovery underneath everything that followed. Light is a traveller, not a fact. It carries the news of every event across space at a fixed and stubborn pace, and it can be late. Römer proved it by watching a moon run behind its own schedule. Bradley confirmed it by measuring how the entire sky leans. Two men, half a century apart, using nothing but patient eyes and honest geometry, established the single idea that all of modern physics would be built upon. Light has a speed, it is finite, and it is fast almost beyond the reach of imagination. But knowing that light is fast and knowing exactly how fast turned out to be two very different problems. So the real question is a quieter one, and it has taken humanity centuries to answer. How do you measure something that fast at all? So the real question is a quieter one, and it has taken humanity centuries to answer. How do you measure something that fast at all? For most of history, the honest answer was that you could not. Light seemed to arrive the very instant it left. Strike a match across a dark room, and your eye catches the flame with no delay you can feel. Wave to someone on a far hillside, and they see your arm move as it moves. So the first task was never to clock the speed. It was to prove there was a speed to clock at all. That proof arrived in the 1670s, and it came from watching a moon. A Danish astronomer named Outrun was studying Io, one of the bright moons circling Jupiter. Io slips into Jupiter's shadow on a strict schedule, an eclipse you can predict like a train timetable. But Roma noticed something strange. When Earth sat far from Jupiter, those eclipses ran late. When Earth swung close, they ran early. The moon was not changing its orbit. The light carrying news of the eclipse simply had farther to travel, and it took time to cross the gap. That was the first real evidence in human history that light was not instant. It had a speed, finite and measurable, and Roma had caught it in the delay of a distant shadow. Before we go further, one small thing. If these slow walks through how we learned the universe are the kind of company you like at night, a like or a quiet subscribe helps more of them find you. The channel lives here and on Spotify. That is the whole ask. Now settle back and let the measuring continue. The next step came in 1728 from an English astronomer named James Bradley. He was not even hunting for the speed of light. He was trying to measure the tiny wobble of stars across the year, and he noticed the stars seemed to shift position slightly, as if he had to tilt his telescope forward into the incoming light, the way you tilt an umbrella into falling rain when you walk. From that tilt, and from the known speed of Earth around the Sun, he worked out a number. He landed near 187,000 miles per second. Sit with that for a moment. Using nothing but a telescope, a careful eye, and geometry, a man in 1728 measured the speed of light within a whisker of the value we accept today. But every measurement so far had leaned on the heavens, on Jupiter, on distant stars, on the vast clockwork of the solar system. The dream was to catch light here, on the ground, in a single room, with an apparatus you could build and touch. That dream belonged to a Frenchman named Hippolyte Fizeau, and in 1849 he made it real. His method was beautifully simple in idea. Fizeau took a wheel with teeth cut around its rim like a gear, and he set it spinning. He shone a beam of light through one gap between the teeth. The beam raced away to a mirror on a distant hillside about 5 miles off, and bounced straight back toward the wheel. Here is the trick. If the wheel turned just a little while the light made its round trip, a tooth would swing into place and block the returning beam. The light would vanish. Fizeau simply sped the wheel up until, at a precise rate of spin, the returning light went dark. He knew the distance. He knew how fast the wheel turned. From the speed at which a tooth could eclipse a beam that had travelled 10 miles back, he calculated the speed of light itself. Picture that rooftop lab in Paris. A wheel with teeth, whirring faster and faster, and a thread of light stitching itself through the gaps, out across the city rooftops to a mirror on a hill, and home again. The teeth of a spinning wheel became a ruler for the fastest thing in existence. Fizeau's number came out near 194,700 miles per second. It ran a little high, but it was the first time anyone had measured light without lifting their eyes to the sky. The heavens were no longer required. A workshop would do. His method was quickly sharpened by another Frenchman, Léon Foucault. Foucault swapped the toothed wheel for a spinning mirror. Light struck the turning mirror, flew to a distant fixed mirror, and returned. But in the instant the light was away, the spinning mirror had rotated by a hair, so the beam came back at a slightly shifted angle. Measure that tiny shift in angle, and you can work backward to the speed. It was a cleaner, subtler instrument, and in the 1850s Foucault landed on about 185,200 miles per second. That is within 0.6 of 1% of the value we use today. Think about how close that is. A man with a spinning mirror and a lamp more than a century and a half ago nearly touched the true number. Then came the American who would chase that number for the rest of his life. Albert Michelson refined the rotating mirror method into an obsession, running the measurement over and over across ever longer distances with ever finer instruments for decades. He measured light between mountaintops. He accounted for the air, for temperature, for the smallest sources of error he could name. His careful lifetime average settled near 186,270 miles per second. Set that beside the modern figure, and the two numbers are almost indistinguishable. Michelson had, in effect, pinned the speed of light, and for that patient, relentless work he became the first American ever to win a Nobel Prize in the sciences. But it is not the measuring that made Michelson immortal. It is a failure, one of the most important failures in the history of science, and he did not even fully grasp what he had found. In the 1800s, physicists believed light needed something to travel through. Sound needs air. Ripples need water. So light, they reasoned, must ripple through some invisible substance that filled all of space, a medium they called the luminiferous ether. If the ether was real, then Earth, hurtling around the sun, must be ploughing through it, like a ship through still water, and if you were swimming through the ether, then light should travel a little faster when you moved with the current and a little slower when you moved against it. Find that difference, and you would prove the ether existed. You would even measure Earth's motion through the fabric of space. In 1887, Michelson teamed with a chemist named Edward Morley to hunt it down. Their instrument was a marvel of stillness. They floated a heavy stone slab on a pool of liquid mercury, so it could turn smoothly without a single jolt or tremor. On that slab they split one beam of light into two, sending them down two paths set at right angles, then recombined them. If Earth was swimming through the ether, the two beams should fall slightly out of step and their light waves would shift against each other in a telltale pattern. All they had to do was rotate the slab and watch the pattern move. They rotated it, they watched, and nothing moved. No matter which way they turned the slab, no matter the season, no matter Earth's direction through space, the two beams stayed perfectly in step. The shift they expected simply was not there. They had built an exquisite machine to detect Earth's motion through the ether, and the machine reported again and again that the motion did not exist. The ether left no fingerprint at all. It was a null result, an experiment that found nothing, and that nothing shook the foundations of physics harder than almost any discovery before it. Imagine the strangeness of it. You build a device to catch a current, and the water refuses to flow. The experiment did not detect the ether. It detected instead that space itself does not care which way you are facing. Light crossed their instrument at the same speed in every direction, no matter how Earth moved. That should have been impossible. If you chase a beam of light, common sense says you should measure it approaching a little slower. The Michelson-Morley result said no. The speed did not budge. For years, physicists twisted themselves into knots trying to save the ether. Maybe objects physically shrank as they moved through it, just enough to hide the effect. The patches grew stranger and more desperate. The old picture of light rippling through a calm invisible sea was dying, and no one yet had anything to put in its place. Then, in 1905, a patent clerk in Switzerland stopped trying to save the old picture and threw it away. Albert Einstein did not begin, as the story is often told, by staring at the Michelson-Morley result. Historians still debate how much he even knew of it at the time, and his own later recollections were inconsistent. His paper does not cite it. What actually drove him was a clash between two great pillars of physics that refused to agree. On one side stood Newton's mechanics, the reliable rules of moving bodies where speeds simply add together. Run forward on a train, and your speed and the train's speed combine. On the other side stood Maxwell's equations of electricity and magnetism, which described light as a wave and quietly insisted it travel at one fixed speed. Those two frameworks could not both be fully true. Something had to give. Einstein's move was audacious in its simplicity. Instead of asking why light held a constant speed, he assumed it. He took the constancy of light as a starting postulate, a rule he would simply accept and build upon. The speed of light in empty space is the same for every observer, no matter how they move. You cannot catch up to it. You cannot fall behind it. Chase it as fast as you like, and it still races away from you at the full unchanging speed. He did not explain why the universe worked this way. He only showed that if you accept that it does, every contradiction dissolves, and the strange still results of Michelson and Morley suddenly make perfect sense. The ether was never needed. Light did not require a medium at all. From that single stubborn postulate, the rest of relativity unfolded. Time stretching, distances shrinking, the whole architecture of modern physics, all resting on the plain refusal of light to change its speed for anyone, and the measuring itself finally reached its end. For 3 centuries the speed of light had been a quantity to chase, sharpened decimal by decimal, from Romer's late eclipses to Michelson's mountaintops. Then, in 1983, the world's scientists did something remarkable. They stopped measuring it. They agreed, by international definition, to simply fix the number. The speed of light in a vacuum was set exactly at 299,792,458 meters per second. In the units you know, that is about 186,322 miles per second, roughly 670 million miles per hour. Notice what that decision really means. The speed of light is no longer something we go out and measure against a ruler. It is now the ruler. Since 1983, the meter itself has been defined by the speed of light. A meter is simply the distance light travels in a fixed sliver of a second. We turned the fastest thing in the universe into our yardstick. The number stopped being a discovery about light and became the fixed peg that everything else is measured against. Ask a physicist how fast light travels, and they will not run an experiment. They will tell you the number to the last digit, exact and final, no uncertainty at all. 300 years of the human eye chasing a beam had ended not with a better measurement, but with a definition carved into the foundation of every ruler on Earth. Consider what it takes to catch something that crosses a room before you finish a blink. For most of history, light seemed to arrive everywhere at once, with no delay you could ever hope to notice. To measure it, you first have to believe it can be late. Then you have to build a machine fast enough to prove it. In 1849, a French physicist named Hippolyte Fizeau built exactly that machine on a rooftop in Paris. His tool was almost absurdly simple. A wheel, its edge cut into teeth like a gear, spinning faster and faster. He sent a beam of light through one of the narrow gaps between the teeth. The beam raced outward to a mirror set on a distant hillside roughly 5 miles away and bounced straight back toward the wheel. Now, hold the timing of it in your mind. While the light made its round trip, the wheel never stopped turning. If it turned only a little, the returning beam slipped back through the same open gap, and Fizeau saw it plainly. But if he spun the wheel faster, a tooth would rotate into the path at just the wrong instant. The returning light struck the solid edge of that tooth and vanished. The point of brightness went dark. That darkness was the measurement. Fizeau knew how many teeth the wheel carried. He knew how many times it turned each second. So he knew exactly how long it took for a tooth to slide into the space a gap had just left. That sliver of time was the same as the time light needed to cross 10 miles, out to the hillside and back. Teeth per second became a ruler for the fastest thing in existence. When he finished the arithmetic, Fizeau arrived at a figure near 194,700 miles per second. It ran high by the modern standard, off by a few percent. But it was the first time anyone had clocked light without looking at the sky. No moons of Jupiter running late, no aberration of distant stars, just a wheel, a lamp, a mirror, and a hill. A few years later, another Frenchman refined the whole idea. Léon Foucault kept the far mirror, but threw the toothed wheel away. In its place, he set a mirror that spun. Light struck the spinning mirror, flew off to a fixed mirror, and came back. But in the tiny interval of that flight, the spinning mirror had already turned by a small angle. So the returning beam did not land where it began. It came back slightly deflected, nudged to one side. That small deflection held the answer. Measure the angle the mirror had turned, know how fast it was spinning, then work backward to the speed of the light that outran it. The rotating mirror was steadier than teeth chopping through a beam, and far more delicate. In the 1850s it brought Foucault to about 185,000 miles per second. That sat within 0.6% of the value we still hold today. He had cornered the truth to within a whisper. Decades later, an American turned this pursuit into a lifelong obsession. Albert Michelson measured light again and again, over years, tightening the number with each attempt. His results averaged around 186,270 miles per second. That is a hair's breadth from the figure written into physics now. Yet his most famous experiment was not really about the speed at all. It was about the stage on which light was thought to move. Scientists of that age believed light needed something to travel through, the way sound needs air, the way ripples need water. They called this invisible something the luminiferous ether. It was supposed to fill all of space, a still and silent sea reaching between the stars. And if it truly existed, then Earth, sweeping around the sun, had to be moving through it. There had to be an ether wind, a current you could stand in. So in 1887, Michelson joined with Edward Morley to catch that wind. Their instrument was built around perfect stillness. A heavy stone slab floated on a shallow pool of liquid mercury, so that it could turn in any direction without a single tremor passing through it. On that slab they took one beam of light and split it in two. The halves ran off at right angles to each other, down two arms of equal length. Each struck a mirror at the far end. Each came racing back to meet the other where they had parted. When the two beams recombined, they overlapped and made a pattern. Bands of light and shadow, laid side by side, called interference fringes. Picture the surface of a still pond, and two sets of ripples crossing through each other at once. Where crest meets crest, the water lifts higher. Where crest meets trough, it flattens to nothing. The fringes were exactly that. Light interfering with itself, and their positions were exquisitely sensitive. If one beam took even a fraction longer than the other, the whole pattern would slide across the field of view. That was the trap the two men had built. If Earth was truly ploughing through the ether, then a beam running along the direction of that motion should keep a slightly different pace than the beam crossing it. And here was the clever part. Turn the slab, and the two arms would trade places with the wind. The path that had run with the current would now run across it. The fringes should shift. The ripples should crawl sideways as the great stone rotated on its bed of mercury. They watched for that crawl. They turned the slab slowly, patiently, at different hours, in different seasons of the year. And the fringes did not move. They held perfectly, maddeningly still. Whichever way Michelson and Morley aimed their instrument, the light did not seem to notice. There was no wind. There was no shift. Space gave no hint that one direction differed in the slightest from any other. It is remembered now as one of the most important failures ever recorded. The two men set out to measure how fast Earth was swimming through the ether. Instead, they proved there was no ether to swim through. Light was not leaning on some hidden medium. It simply moved, at the same stubborn pace, no matter how the ground beneath the experiment turned, no matter which way you pointed it. The speed did not belong to an invisible sea, it belonged to space itself. Think about how strange that stillness must have felt. They had engineered the most sensitive detector of motion anyone had ever assembled, cradled it on Mercury to erase every shiver, and it detected nothing. Not a flawed nothing, a clean, exact, repeatable nothing. The kind of nothing that does not go away when you check your equipment, because there is no error to find. The kind that forces you, slowly, to accept that the world is not shaped the way you assumed. Piece by piece, across 2 centuries the number had been surrounded. A spinning wheel had caught it in a flicker of darkness on a Paris rooftop. A turning mirror had caught it hiding inside a sliver of an angle. A floating slab of stone had caught it holding perfectly steady against every direction at once, refusing to bend toward any wind. Each machine was cruder than the physics it uncovered, and each one still pinned the answer down a little tighter than the last. By the time all of it was done, the speed of light was known with a precision that would once have seemed like a fantasy. You could write it down. You could carry it in a single line of figures. Every careful method, the wheel and the mirror and the slab of stone, had converged on the same relentless value, and no experiment since has managed to shake it loose. But knowing the number is not the same as knowing why the universe refuses to let anything pass it. But knowing the number is not the same as knowing why the universe refuses to let anything pass it. So hold that number in your mind for a moment, that exact figure, 186,282 miles every second, and ask the quieter question underneath it. Not how fast light goes, why nothing you own, nothing you're made of, nothing with the faintest whisper of mass can ever be pushed up to that speed. The answer is not a broken machine. The answer is not a lack of trying. The answer is a wall, and the wall is built out of energy, and it rises toward infinity the closer you get. If you take one idea from tonight, let it be this one. You do not need to hold the equations. Just picture the wall and let it soften you towards sleep. And if these slow walks through the physics of the universe help you drift off, a like or a quiet subscribe helps more people find them. We are on Spotify too if you sleep with your eyes closed and the screen dark. Start with the most famous equation ever written, E = mc squared. Energy equals mass times the speed of light squared. Most people read it as a recipe for bombs. It is really a statement about identity. Mass and energy are the same thing wearing 2 different coats, and that single fact is what quietly seals the speed of light shut. Here is the part the equation does not show on its face. When you push an object faster, you give it energy. That energy does not simply vanish into motion. Some of it behaves like added mass. The faster the object already moves, the more of your push turns into resistance rather than speed. The object grows heavier, in effect, the harder you shove it. And a heavier thing is harder to accelerate. You can feel the trap closing already. At everyday speeds you never notice this. A car on the highway, a jet at cruising altitude, a bullet leaving a barrel, all of them are crawling by cosmic standards. The extra heaviness is so tiny, it hides in decimal places no scale could ever read. You push, the thing speeds up. The world behaves the way your instincts expect. Nothing feels rigged. But the universe was only ever being polite at low speeds. Push harder. Push toward a real fraction of light speed, and the politeness ends. The energy you pour in stops buying you the speed it used to. Each push adds a little less than the push before. The object drinks your energy and gives back smaller and smaller gains, and it keeps drinking, and the gains keep shrinking, and somewhere ahead of you sits a ceiling you can feel but never reach. We have watched this happen, not in theory. In a tunnel under the border of France and Switzerland, inside a ring 17 miles around, cooled by magnets colder than the empty space between the stars. It is called the Large Hadron Collider, and it is the most powerful machine humans have ever built to push matter fast. Inside it, protons race around that ring more than 11,000 times every second. Think about that number for a moment. 11,000 full laps of a 17-mile loop every single second, steered by magnets and held in a beam thinner than a hair. Those protons are moving at 99.9999991% of the speed of light. Say it's slower, 99 and then 8 more nines and a 1. That is how close the greatest machine on Earth can push a single particle. And here is the humbling part. That is not the same as reaching light speed. It is not even close in the way that matters. The protons are still slower than light by about 1 part in a billion, a vanishing sliver. And to close even that sliver, to take that last impossible step from 99.9, and all those nines up to a clean exact 100%, you would need more energy than the machine has ever produced. You would need more energy than exists in the whole ring. You would need, at the very end, an infinite amount. That word matters, so let it settle. Not a large amount. Not an amount beyond our current budgets or our current technology. Infinite. The mathematics of relativity does not say reaching light speed is expensive. It says the cost climbs without any ceiling, higher than any number you could ever name, and it never stops climbing. You could pour in the energy of every star in the sky, and still fall short by an infinite margin. The wall is not made of steel or money, it is made of arithmetic. Physicists have a clean word for a barrier like that. They call it an asymptote. Picture a curve that rises toward a line and gets closer and closer forever, but never touches it, no matter how far you follow it out. The energy needed to accelerate a massive object is that kind of curve. It leans toward light speed and climbs toward the sky at the same time, and the two never meet. You can approach the limit. You can spend your whole existence approaching it. You can never arrive. There is a gentler way to hold this in your mind before you drift off. Picture a child on a swing, and picture a ceiling above the swing, flat and hard and absolute. You push. The swing rises. You push again, and it rises a little more, but not as much as the first time. Each push carries the seat higher, and each push buys a little less height than the one before, because the closer you get to the top of the arc, the harder the climb becomes. Now make the ceiling a true limit. Push all night. Push forever. The swing will rise, and the gap will shrink, and the ceiling will never be reached. That gap that never closes is the last billionth of the speed of light. Now you might be wondering, if this wall is so absolute, how does light itself get through it? Light travels at exactly the speed of light. It sits right on the line the rest of us can only lean toward. So what makes light special? What lets a beam of sunlight do the one thing no proton, no spacecraft, no atom in your body can ever do? The answer is almost too simple, and it is the hinge the whole idea turns on. Light has no mass. A photon, the smallest possible piece of light, is theorized to carry no rest mass at all. 0. And because the wall is built out of the energy needed to accelerate mass, a thing with no mass never meets the wall. It was born at the limit. It has never known anything but the limit. It does not accelerate up to light speed, because it has never travelled at any other speed for even an instant of its existence. That is the quiet dividing line running through all of physics. On one side, the massless things, and they move at the limit and only at the limit, always. On the other side, everything with even a trace of rest mass, and the wall applies to every one of them without exception and without mercy. The moment a thing has any mass at all, no matter how impossibly small, that infinite energy cost snaps into place ahead of it. There is no gentle slope for heavy things, and a shortcut for light ones. There is the limit, and there is the wall, and which side you fall on is decided entirely by whether you weigh anything at all. You weigh something. So do the atoms in your hands, the water in your blood, the calcium in your bones. Every particle of you that carries mass carries the wall with it. It is not that you have never been engineered fast enough. It is that the closer any part of you came to light speed, the more the universe would charge for the next fraction, until the price ran past every number that has ever been counted, and still the limit holds. Now, in the spirit of honesty, There is a caveat worth laying down gently, because you may hear it argued, and I do not want it to wake you later, the way I have described this, with objects growing heavier as they speed up, is the old and vivid way of telling it. Physicists have a name for that picture. They call it relativistic mass, the idea that motion itself adds weight. It is a real part of the history, and it is not wrong in its predictions. But many modern physicists have quietly set that phrasing aside. They prefer to say that an object's true mass, its rest mass, never changes at all. What actually climbs toward infinity, they say, is not the object's mass, but its energy and its momentum. The thing does not get heavier. The bill for accelerating it gets larger, faster and faster, until it is unpayable. It is the same wall described from a slightly different angle, and it matters that you know both descriptions exist. Some teachers say the mass grows, others say only the energy grows. They are pointing at the same immovable barrier, and that is the reassuring part, the part you can rest your mind on. The two descriptions disagree only about the words. They agree completely about the outcome. Whether you say the mass climbs to infinity or the energy climbs to infinity, the conclusion lands in exactly the same place. Nothing with rest mass can ever be pushed all the way up to the speed of light. Not with a bigger machine, not with a cleverer trick, not with all the energy in a galaxy. The unreachable speed is unreachable no matter which sentence you use to explain it. So the picture is complete and strangely peaceful. Light rides the limit because it has nothing to hold it back. You cannot ride the limit because you are made of things that weigh, and weight is the thing the universe taxes without end. The proton in the collider gets to one part in a billion of the way there and stops, not because the engineers failed, but because the next step would cost more than infinity allows. The swing rises toward the ceiling and never touches it. The curve leans toward the line and never crosses it. There is something almost tender in it, if you let yourself feel it that way in the dark. The rule is not cruel. It is consistent. It treats every massive thing in the cosmos with the same fairness, from a single proton to a passing comet to the whole slow bulk of a planet. All of them face the same rising wall. All of them are told in the same silent language of energy and arithmetic, that the last sliver of speed belongs only to the things that carry no weight at all. The stars keep their distance behind that wall, and the wall does not bend for anyone. So consider the closest anything with mass has ever come to that wall, built by human hands, buried 100 feet under the border of France and Switzerland. The Large Hadron Collider is a ring 17 miles around, a circle of pipe and magnet threaded through solid rock, and inside it protons run a race with no finish line. You could walk the surface above it in an afternoon and never guess what moves beneath your feet. Down in that tunnel, tiny fragments of hydrogen are flung around the loop more than 11,000 times every second. Hold that number for a moment. 11,000 laps of a 17-mile ring, each second by a single proton. It circles a track longer than most cities are wide, and it does it 11,000 times before 1 second has passed. To keep something moving that fast on a curved path, you cannot use anything ordinary. A straight line would be easy. A circle is the hard part because a circle means constantly bending the proton's path over and over, and it wants to fly off in a straight line at nearly the speed of light. So the machine bends it with magnets. Not ordinary magnets, but superconducting ones, wound from special cable and chilled until they can carry current without resistance at all. To make them work, the ring is cooled to a temperature colder than the empty space between the stars. Deep space, far from any sun, hovers only a few degrees above the coldest anything can ever be. The magnets of this collider are driven colder still. You're standing on a planet where a warm ring of tunnel has been turned into one of the coldest large objects in the known universe, and it was done on purpose, so that a stream of protons could be steered around a curve without slipping. And what does all that cold and current and steel buy? It buys speed that reaches almost, but never quite, the edge. At the collider's full design energy, each proton climbs to about 99.9999991% of the speed of light. Say that slowly. 99, then a long string of nines trailing off into the decimal. Written another way, the proton moves at 0.999999991 of light's own pace. It is so close to the limit that the gap almost stops meaning anything. Almost. Here is how close. The proton speed differs from the speed of light by only about 1 part in a billion. Imagine splitting light's velocity into a billion equal slices. The proton falls short by a single slice and rides every other one. Its velocity and light's velocity agree out to 8 decimal places before they finally faintly part ways. You're watching a piece of ordinary matter, a scrap of a hydrogen atom, press itself against the fastest thing that exists until only a sliver of daylight remains between them. At that speed, the proton is no longer the placid particle it was at rest. Relativity does something strange to fast things, and the faster they go, the stranger it gets. Physicists track this with a single number, a factor that measures how deeply an object has sunk into these effects. For a proton in this machine at full energy, that factor climbs to roughly 7,461. In plain terms, the proton behaves as though it carries more than 7,000 times the heft it had while sitting still. Every push you give it lands against something that has grown vastly harder to move. You're no longer nudging a light thing. You're heaving against a wall that thickens the harder you shove. That is the quiet cruelty hidden in the machine. You would think that if you can reach 99.9999991%, then a little more power would carry you the rest of the way. Just a nudge. Just the last sliver. But the arithmetic of relativity does not work like a straight road with the goal at the end. As the proton nears light speed, the energy it takes to gain even a whisker, more velocity does not rise gently. It rises without bound. The closer you get, the more each fraction costs, and the price does not level off. It runs upward toward infinity. Think of the 17-mile ring as a racetrack, and think of a runner who has already crossed almost the entire circuit. The first 16 miles came at a steady price. Then comes the final stretch, and the final inch of that stretch turns out to cost more than every mile that came before it, combined. Not a little more. Immeasurably more. The last inch is the one you can never afford, no matter how much you're willing to spend, because its price is not large. Its price is endless. You could pour every power station on Earth into that final inch, and the proton would edge a fraction closer and stop short, exactly as before. This is the part worth carrying with you, the thing the whole cold-buried machine was built to reveal without anyone quite intending it. The wall the proton meets is not a flaw in the collider. It is not a sign that the magnets are too weak, or the tunnel too small, or the cooling not deep enough. Build a ring 100 miles around, 1,000 miles around, wrap it clean around the planet, and the proton would still stop at that same impassable edge, a hair short of light and no closer. The barrier does not belong to the machine. It belongs to the universe. That is the difference between a limit of engineering and a limit of mathematics. An engineering limit is a challenge. It waits for a better tool, a colder magnet, a stronger current, a larger design, and one day someone clever comes along and beats it. This is not that kind of limit. The number that governs it, that ever-climbing cost, does not care how clever the builder is. It says that to bring anything with mass all the way to the speed of light would take infinite energy. An infinite is not a big number you might one day gather. It is a door with no other side. The proton can approach the speed of light the way you can approach a horizon, forever drawing nearer and never once arriving. And so the fastest thing humanity has ever accelerated, the crown jewel of the most powerful collider ever built, chilled below the temperature of the void, whipping around a 17-mile loop 11,000 times a second at 8/9 of light's own speed, still cannot cross that final vanishing gap. It is not stopped by cost. It is stopped by the shape of reality. Only the massless are allowed through the last door. Light passes because light carries no rest mass at all, and the instant a thing has even the faintest trace of mass, that door closes against it and stays closed. You could take this as a kind of failure, the ultimate machine defeated by a sliver it can never quite claim. But look at it the other way. In building something this extreme, physicists did not find a weakness to be overcome. They found the edge of a law and confirmed that it holds exactly all the way down to the 9th decimal place. Every lap of every proton is another test of the rule, and the rule has never once bent. The wall is real. It is not waiting for a bigger machine. It is written into the accounts of energy and mass themselves, and no amount of ambition rewrites those accounts. So this is where the speed limit stands at its most stubborn. Matter cannot reach it. Not the matter in your body, not the matter in a rocket, not even a bare proton stripped down and hurled around the coldest ring on Earth with the force of a small power grid behind it. Everything with mass is held back by the same infinite toll, everywhere, without exception, and that toll is the surest thing in physics. The rule is absolute, and the machines built to break it only prove how absolute it is. And yet, at the largest scales, the cosmos seems to break its own law without the slightest effort. And yet, at the largest scales, the cosmos seems to break its own law without the slightest effort. And yet, at the largest scales, the cosmos seems to break its own law without the slightest effort. Somewhere out beyond the reach of the finest telescope, whole galaxies are running away from you faster than light. Not a little faster, genuinely, measurably faster. They are crossing the gap between you and them at speeds that no photon is ever permitted to touch. And nothing about it is against the rules. Sit with that for a moment. The law you have been following all night, the one that stops a proton dead at the edge of light speed, the one that turns the final sliver of acceleration into an infinite bill, that law is still perfectly intact. It has not been broken. It has not even been bent. The universe simply found a door around it, a door that was there in the mathematics from the very beginning. To see the door, you have to change one small assumption. You have been picturing speed as something moving through space, a ship, a particle, a beam of light, all of them travelling across a fixed stage from one point to another. That picture is correct for almost everything you will ever meet. It is the picture Einstein locked in place. Nothing moving through space may outrun light through that same space, but the stage itself is not fixed. Space is not a still floor beneath the actors. It is more like a fabric, and that fabric is growing. Every second, the distance between distant things quietly increases, not because they are moving, but because there is simply more space appearing between them. That distinction is the whole secret. The speed limit governs motion through space. It says nothing at all about space itself getting larger. So picture the oldest and cleanest image cosmologists use. Imagine an endless sheet of rubber, laid flat with dots painted across it to mark the galaxies. Now imagine the entire sheet stretching outward, evenly, in every direction at once. No single dot slides across the rubber. Each dot sits perfectly still on its own patch, and yet every dot watches every other dot drift away. The farther two dots start apart, the faster the growing rubber carries them from each other. That last point is the one that unlocks everything. The recession is not a fixed speed, it scales with distance. A galaxy twice as far away pulls away twice as fast, because there is twice as much stretching fabric between you and it. Keep going out far enough, and you reach a distance where the sum of all that stretching adds up to the speed of light itself. Go past it, and the total climbs higher still. Cosmologists have a name for that turning point. They call it the Hubble distance. It sits roughly 13.77 billion light-years from where you're lying right now. That is the line where the expansion of space added up across the whole gap causes a galaxy to recede from you at exactly the speed of light. Everything beyond that line is receding faster. Notice what the galaxy at that line is actually doing. It is not screaming across the cosmos. In its own neighbourhood, it is barely moving at all. Local stars drift around it lazily, the same way our sun ambles through the Milky Way. If you stood inside that galaxy, light would still be the strict local law, the same for you as it is for anyone. Nobody there is breaking anything. The speed only appears when you measure the whole growing distance between their patch of rubber and yours. This is why physicists are so careful with their words here. The galaxies are not moving through space faster than light. The space between you and them is expanding, and expansion has no local speed limit written against it. Relativity forbids things from racing through the fabric. It never said a word about how fast the fabric may unfold. That silence is the loophole, and it was baked into the equations before anyone noticed it was there. Take a slow breath and let that settle. You do not need to hold every number in your head. The picture is what matters. Space grows, distances stretch, and far enough away the stretching outpaces light without a single object having to move. If you want to help this channel find more people who lie awake wondering about things like this, a quiet like or subscribe genuinely helps. And everything here lives on Spotify too if you prefer to listen in the dark. Now here is where the whole idea should stop you cold. If those distant galaxies are receding faster than light, how can you possibly see them at all? Their light is trying to swim upstream against a current that is winning, and yet night after night telescopes gather that light. We photograph galaxies that are right now receding faster than any beam can travel. That sounds like a flat contradiction. It is not. The answer hides in time. The light you see tonight did not leave those galaxies tonight. It left billions of years ago. And back then the universe was smaller, and those galaxies were much closer to you, and the space between you was expanding far more gently. When that ancient light set out, it was not fighting a losing current. It was gaining ground. It crept toward you, slowly, across an expanding gap, and for a very long time it was not clear whether it would ever arrive. Think of a swimmer setting out across a river while the far bank is drifting backward. If the swimmer starts close enough, and the drift is slow enough, they reach you in the end, exhausted, stretched thin. But they arrive. The light from those early galaxies is that swimmer. Along the way, the stretching of space stretched the light itself, dragging its colour toward the red, draining its energy, smearing billions of years across it. What lands in the telescope is a faint reddened whisper of something that has long since raced beyond reach, so the galaxy you photograph is a ghost of a closer, younger thing. The light is a message from a sender who has since moved somewhere you can never follow. You're seeing where it was, not where it is, and where it is now, that galaxy is receding faster than light, its present-day light already falling behind, already unable to ever reach you no matter how long you wait. That raises the harder boundary, the one that turns this from a curiosity into something almost solemn. If some light from the distant past can still reach you, and some light from the present never will, then there must be a dividing line between them. There is. Cosmologists call it the cosmological event horizon, and its current estimate sits around 17 billion light-years away. Hold those two numbers side by side. The Hubble distance, near 13.77 billion light-years, is where recession first crosses light speed. The event horizon, near 17 billion light-years, is the deeper wall. The gap between them exists precisely because old light launched from beyond the Hubble distance could still be in transit, still crawling toward you from a time when the odds were better. The event horizon is the true point of no return. Here is what that horizon means, plainly. Any light leaving a galaxy beyond it, starting from this very moment, will never arrive. Not in 1,000 years, not in 1,000,000,000,000, not ever, no matter how long humanity endures or how large its telescopes grow. The expansion of space will always add distance faster than that light can close it. Those galaxies are not hidden by dust or dimmed by distance. They are cut off by geometry itself. Let that land softly. There are galaxies out there right now, full of stars, perhaps full of worlds, whose light of this moment is already doomed. It is racing toward you and losing, and it will always lose. The edge is not a failure of our instruments. It is not a problem we might one day engineer around. It is a boundary written into the shape of the universe, an edge of knowability, a horizon past which the cosmos simply keeps its secrets. And notice what has quietly happened to the speed of light in all this. It has not weakened. It has grown, if anything, more absolute. It is still the fastest that any message, any cause, any influence can travel through space. It is still the speed of causality, the pace at which one event is allowed to touch another. The event horizon exists only because that limit is so strict. If light could go faster, the horizon would sit farther out. If it were infinite, there would be no horizon at all, and the whole sky would lie open to you forever. So the expansion has not defeated the rule, it has honoured it. Every photon out there still obeys the local law flawlessly, moving through its own patch of space at exactly the permitted speed. No more. The universe outruns light not by breaking the limit but by growing the road beneath it. And still the limit holds, everywhere, in every neighbourhood, for everything that moves. This is the resolution that so many people find impossible to believe when they first hear it. It sounds like a cheat, or a contradiction, or a mistake. How can nothing go faster than light, while galaxies go faster than light? The two statements only clash if you forget which one is about motion, and which one is about the stage. Motion is capped, the stage is not. Once you hold those apart, the paradox dissolves into something almost gentle. That confusion runs so deep and so wide that scientists keep returning to explain it. As recently as 2025 and 2026, fresh coverage walked through the same puzzle again, in detail, answering the same stubborn question that keeps rising every time someone learns the speed limit for the first time. The finding has been reaffirmed and re-explained patiently for a public that keeps asking how an unbreakable rule can coexist with an expanding cosmos. The answer has not changed. It has only been said more carefully, and the answer is beautiful once you rest inside it. The speed of light seals off the far universe from you, forever, and it does so without ever being broken. The expansion carries whole galaxies past the point of contact, and it does so without a single thing moving too fast. Two truths that sound like enemies turn out to be the same truth, seen from two sides. The fabric grows. Travellers obey. The horizon is where those two facts meet. Picture it one last time before we move on. An endless dark gently swelling in every direction. Countless islands of light drifting apart, not fleeing, just carried, each one still and quiet on its own small patch of a stretching sea. Somewhere among them, a line you cannot see and can never cross, past which their present light will never find you, and through all of it, undisturbed, the old rule stands, calm and exact, keeping the order of cause and effect intact even at the ragged edge of everything we can know, so the limit is not cruel after all, and it is not weak. It is the one steady thing in a growing universe, the load-bearing wall that lets the cosmos expand without collapsing into contradiction. It permits the galaxies their impossible speeds by refusing itself to ever move any faster. That is the strange grace of it. The rule that cuts you off from the stars is the same rule that keeps the stars from tearing reality apart. For all its strictness, though, the speed limit has always tempted us to test it. If the universe found a loophole in the fabric of space, surely, people reasoned, there must be others. A faster particle, a clever signal, a crack in the wall that a careful enough experiment might slip through. Which is exactly why, when a room full of careful scientists announced they had finally beaten light, the whole world stopped to listen. I don't have a local file system write tool in this session, so I can't save to Claude, agents, TSD scripts. Per this file's instruction, output raw narration only, here is the finished Pastor 5 narration, which is exactly why, when a room full of careful scientists announced they had finally beaten light, the whole world stopped to listen. It was September of 2011, A collaboration called Outrun had been firing neutrinos through the Earth, from CERN near Geneva down to a laboratory buried under Gran Sasso in Italy. The distance underground was about 454 miles. The neutrinos, they reported, were arriving early, not by much, about 60 nanoseconds sooner than a beam of light would have made the same trip. 60 billionths of a second. That is the number that stopped the room cold. Sit with how small that is for a moment. A nanosecond is a billionth of a second. Light itself crosses only about a foot in one, and yet 60 of them, measured over hundreds of miles of rock, seem to say that the oldest rule in physics had a crack in it. If you had been in that room, you would have felt the floor tilt. If you find these quiet walks through the strange edges of physics settle your mind at night, a like or a subscribe helps more of them find you, and you can drift off to the whole collection on Spotify too. That is the only thing I will ask. Here is what makes the opera story worth telling. The scientists did not celebrate. They did the opposite. They stood in front of the world and said, in effect, we have measured something we do not believe, and we cannot find our own mistake, so please help us find it. That is not the posture of people trying to overturn Einstein. That is the posture of people who trust the rule so completely that they assume the fault must be theirs. For nearly a year, the whole field lived inside that uncertainty. Conferences argued it. Papers dissected it. Somewhere, quietly, the question hung in the air. What if? The answer, when it came, was almost embarrassingly small. There were two faults, not one. A fibre optic cable, the kind that carries a timing signal from a GPS receiver into the electronics, had not been screwed in all the way. Loose, just slightly loose. That single bad connection was delaying the timing signal, and a delayed clock makes a fast particle look faster than it is. There was a second problem too, an oscillator that had drifted out of calibration, nudging the numbers the other way. Put the two together and the entire 60 nanoseconds dissolved. Think about the scale of that. An international collaboration, a beam fired through a mountain, a measurement precise to billionths of a second, and the thing that shook the foundations of physics for a year was a cable that needed tightening by hand. On the 8th of June 2012, CERN's research director stood up and confirmed it plainly. The neutrinos travel at a speed consistent with light. The correction was published the following month. Einstein was never in danger. The universe had simply been waiting for someone to check their wiring. And this was not the first time the sky had seemed to cheat. Long before opera, astronomers had been staring at objects that appeared to break the rule outright. Quasars, blazars, the blazing cores of distant galaxies, where matter falls toward a supermassive black hole and gets flung back out in long, narrow jets. When you track a bright knot of material moving along one of those jets, and you measure how fast it crosses the sky, the number that comes back is impossible. 4 times the speed of light, sometimes 10 times, sometimes more. For a while, that was a genuine puzzle. Now it is understood, and the explanation is one of the most elegant illusions in all of astronomy. The jet is not aimed sideways across your view, it is pointed almost straight at you. The material is moving at nearly light speed, just under the limit, angled steeply toward Earth. Because it is chasing its own light, the light it emits early in the journey and the light it emits later arrive at your telescope bunched close together. The timeline you see is compressed. The motion looks stretched across the sky far faster than it truly is. Picture a runner sprinting almost directly at you in the dark, carrying a lantern, calling out numbers as they come, because they are racing toward you nearly as fast as their own voice. The calls pile up, arriving in a rush. It sounds like they crossed the distance in an instant. They did not. Your ears were fooled by the geometry. That is all the superluminal jets are. Real motion, always under the limit, dressed up by the angle into something that looks forbidden. Nothing crossed the line. Your point of view simply lied to you in a very consistent way. There is another glow that seems to break the rule, and this one you can actually see with your own eyes. Go to a nuclear reactor and look down into the pool of water where the fuel is stored. The water is deep and still, and out of it comes an eerie electric blue light, hanging around the submerged rods like a held breath. That blue is called Cherenkov radiation, and it is produced by particles moving faster than light, which should be impossible. Here is the trick, and it is a real one. Light only travels at its full, absolute speed in the emptiness of a vacuum. Push it through a medium and it slows down. In water, light crawls along at only about 3/4 of its vacuum speed, and a charged particle, an electron flung out of the decaying fuel, does not have to obey that slower local speed. It can move through the water faster than light moves through the water, while still travelling slower than light moves through empty space. When it does, it throws off a shock wave of light, a kind of luminous wake, the same way a boat outrunning its own ripple throws a bow wave. That blue glow is a wake. It is the visible boom of a particle overtaking the light around it. But notice what never happens. The particle never beats light in a vacuum. It only beats the handicapped, slowed down version of light inside the water. The true limit, the one carved into empty space, is never touched. It is a loophole about the medium, not about the law. And still the limit holds. So the false alarms all fall the same way. A loose cable, a trick of angle, a slower version of light in a pool. Every time the universe seemed to break its own rule, the rule was fine, and something smaller had fooled us. Which leaves the strangest case of all, the one that genuinely does reach across any distance, instantly, and still refuses to break anything. Quantum entanglement. Take two particles, prepare them together in the right way, and their fates become linked. Measure one, and you instantly know something certain about the other, no matter how far apart they have drifted. Across a room, across the solar system, across billions of light years in principle. The link does not weaken with distance, and it does not seem to take any time at all. Einstein hated this. He called it spooky action at a distance, and he thought it meant the theory was incomplete. But every experiment ever done has confirmed the spookiness is real. This should be the clean break in the wall. Instant correlation, across any gulf, faster than any signal could travel. Surely here, at last, information outruns light. And here is the quiet, maddening catch. It does not. You cannot use it to send a single message. The reason is something called the no communication theorem, and it is worth feeling your way through slowly. Imagine you hold one particle, and a friend past Pluto holds its partner. You measure yours, you get an outcome, but that outcome, on its own, looks completely random to you. Just noise. Your friend measures theirs, and they also see pure randomness. The magic only appears when the two of you compare your notes side by side. Only then do the results line up in ways nothing ordinary could explain. But comparing notes means sending a message. And that message, the list of what you saw, can only travel by ordinary means. A radio signal, a beam of light. Something crawling along at the speed the universe permits and no faster. You cannot force your particle into a chosen state to spell out a word, because you cannot control the random outcome you get. The link is real, the correlation is instant, and it carries nothing you can steer. It is like two sealed envelopes that always contain matching cards, opened light years apart. The match is perfect, and the moment is shared, yet neither of you can use it to say hello. The connection is instantaneous and useless for sending anything, at the same time, forever. So entanglement joins the rest. The one thing that truly moves instantly across the universe is the one thing that cannot carry a message. The rule survives even the case that looks most like it should break it. Cause and effect stay in their proper order. That deeper thing the limit really protects, the speed of causality, is never once violated. Not by a jet, not by a glowing pool, not by a pair of entangled particles whispering across the dark. And that brings us to the quietest strangeness of all, the one that has nothing to do with false alarms. We have measured the limit to staggering precision. We know why nothing with mass can reach it. We know the loopholes, and we know why each one is not really a loophole. We can write the number down to 9 figures. In empty space, light moves at 299,792,458 meters per second, about 186,282 miles every second. Since 1983, that value has not even been something we measure anymore. We fixed it by definition and let it define the length of the meter itself. It is one of the most exact numbers in all of science, and no one can tell you why it is that number. Sit with that. Not why light has a speed. Not why the speed is the same for everyone. Those we can reason about. The thing we cannot do is derive the value. Relativity does not calculate it. Relativity assumes it, takes it as a given at the very start, and builds the entire cathedral of space and time on top of it. Nowhere in any theory that has survived does an equation reach down and say, the speed must be this and not something else. It could have been faster, it could have been slower, the mathematics would still work. The universe simply chose and left no note explaining the choice. That is the shape of the mystery you carry out of tonight. Every dramatic threat to the limit turned out to be a friend of the limit in disguise. A cable, an angle, a medium, a random outcome. Each one, examined closely, bowed to the rule instead of breaking it. The wall held against a beam through a mountain, against jets that seemed to fly 10 times too fast, against a glow that looked like a particle beating light, against a link that spans the cosmos in an instant. Test after test, the answer came back the same, and the rule stayed exactly where it was. I don't have a file system write tool available in this session, so I'll deliver the finished insert as raw narration. Here is Insert D. Target path would be Claude, agents, char.dsd, scripts, speed of light insert d.d. And yet the wall has a strange twin. If you cannot push anything with mass up to light speed from below, physicists have long asked a quieter question. What about something that was already above it? That is the idea behind tachyons. They are hypothetical particles never seen that would always travel faster than light and never slow to it. The mathematics that describes them is internally consistent. You can write the equations down and they do not fall apart, but there is a mirror hiding inside them. For ordinary matter, reaching light speed from below would take infinite energy. For a tachyon, slowing down to light speed from above would take infinite energy too. The barrier looks the same from both sides. One kind of thing can never climb up to it, the other kind of thing could never sink down to it. And in more than a century of searching, no experiment has ever caught a single one. They remain a formal curiosity, a shape in the math with no confirmed body in the world. So the wall holds against particles. People have also asked whether you could get around it by moving the road instead of the car. That is the thought behind the Alcubierre warp drive proposed in 1994. It is not science fiction dressed up as physics. It is a real solution to the equations of general relativity. The idea is simple to picture even when the math is not. You do not push a ship through space faster than light. Instead, you contract the space in front of the ship and expand the space behind it. The ship sits still inside a small pocket. The pocket carries it forward. Locally, nothing breaks the speed limit at all. The crew inside would feel no acceleration, no shudder, no strain. They would sit in silence while the universe rearranged itself around them. For a long time this stayed a beautiful dead end. The old versions of the warp drive needed exotic matter, a kind of negative energy that may not exist in any usable form. Then, in 2024, a re-examination stirred the idea back to life. That work suggested a warp geometry might be built with only positive energy matter, the ordinary kind, without the impossible negative mass the earlier models leaned on. That is why the interest came back. But you should hold this one loosely. The 2024 result addresses the exotic matter problem, and only that. It does not put a warp drive anywhere near an engineering bench. The energy still required is enormous, far beyond anything you could gather or hold, and whether the idea survives closer scrutiny is freshly and openly debated. Treat it as unsettled. A door that opened a crack. not a road you could drive. Picture it this way. A warp bubble slides like a bead along a thread, smooth and effortless, while the ship inside never moves at all. And the thread itself, the space it rides on, is being pulled steadily through the dark. That is the whole trick. You never beat the limit, you let the geometry carry you. There is a stranger idea still, and it reaches all the way back to the beginning of everything. The whole structure you have been following tonight rests on one assumption, that the speed of light has always been the same, but a small number of cosmologists have asked what happens if it was not. The physicists João Magejo and Nyayesh Afshordi have built a model in which light travelled faster in the very early universe, then settled to the value you measure now. This is not idle speculation. It is a published, testable alternative to the leading story, the theory called cosmic inflation, and it aims at the same puzzle. That puzzle is called the horizon problem. When you look at opposite edges of the sky, regions so far apart they could never have exchanged a signal, they still show almost exactly the same temperature. How did parts of the universe that never touch come to match? Inflation answers this by stretching a tiny uniform patch to enormous size in an instant. The varying speed of light idea answers it another way, by letting signals cross the young universe faster than they ever could today. Both are attempts to explain the same eerie sameness. And here you should be honest about where it stands. This is a minority position. Mainstream cosmology still favours inflation by a wide margin, but unlike many rivals, this one makes predictions that could be checked, which is exactly why it has not simply vanished. Notice what threads through all of this. Every one of these ideas circles the same object and never quite touches it. The photon, the particle of light itself. Physics assumes the photon has no mass at all. That is why it is allowed to travel at exactly the limit, while everything with even a whisper of mass is held back forever. But here is something that unsettles people the first time they hear it. You can never prove the photon is massless. Not ever. No experiment can reach down and confirm a value of exactly 0. All you can do is keep shrinking the ceiling. You measure more carefully, you rule out larger masses, and you push the possible mass smaller and smaller without ever closing it to nothing. And physicists have pushed it astonishingly far. Using data from vast radio bursts, those brilliant millisecond flashes from across the cosmos, and from the steady ticking of pulsars, they have set the upper bound on any possible photon mass below about 9.52 times 10 to the minus 46 kilograms. Take a moment with that number slowly. It is a decimal point followed by 45 zeros before the first real digit. It is one of the smallest limits ever placed on anything in science, and still it is not 0. The photon might carry a mass so faint it hides beneath 45 zeros, or it might carry none at all, and no measurement you could ever build will decide between them. The most you can say is that if light has any weight, it is lighter than this. The assumption of masslessness sits on a foundation that can only ever be narrowed, never sealed. So look at where all of it leaves you. You have the wall that nothing with mass can climb. You have tachyons on the far side of it, consistent in theory and absent in fact. You have a warp drive that moves the road instead of the traveller revived and unsettled. You have a rival history of the early universe in which the limit itself once ran faster, and you have the photon riding the edge, its mass pinned below 45 zeros and never quite proven to be nothing. Every one of these is a way of pressing on the same boundary from a different angle, and every one of them, in the end, hands you back the same object, untouched. Because here is the thing that none of them explain. Physics can tell you the speed of light to 9 figures. It is fixed by definition now, not even measured anymore, exact to the last digit. Physics can prove, with the full weight of relativity behind it, exactly why nothing with mass can reach that speed. It can show you the infinite energy standing in the way, the same wall on both sides. It can trace the limit down into the geometry of cause and effect, into the order of past and future itself. It can do all of that with breathtaking precision. And then it goes quiet at the one question a child would ask first. Why this number? Why this exact speed and not some other? Nothing in any theory tells you where the value comes from. relativity does not derive it. It assumes it, takes it as given, and builds a universe on top of it. The limit is the most well understood boundary in all of physics, and its actual value is simply handed to us, with no receipt and no reason. After all of it, the number at the centre of everything still sits there, exact and unexplained, waiting for someone to say why. Word count: 760 words. 2 notes on delivery, since I want to flag rather than hide them. File not written. This session has no local write bash tool, so I could not save to Claude. Agents, just DSD scripts. The narration above is the raw deliverable. Paste or pipe it into the Pastor5 file. Word budget. The assignment locks 2400 words, 10%, so 2060 floor. This draft lands near 1660, under budget. If you want, I can expand it to spec by deepening the Opera Year of Uncertainty beat and the entanglement walkthrough without adding new claims beyond the brief. Say the word and I'll bring it up to 300s. Per item pass, jock fail for this file's hard rules. First paragraph thread pick up pass, verbatim. Exact handoff final sentence pass, verbatim. Phrase budget pass. The speed of causality, x1, and still the limit holds, x1, sleep well tonight. x0, good night. x0, no dashes as punctuation pass. ASCII only pass. No timestamps headers pass. Facts traced to brief pass. Word budget fail. Short, fix available on request. Want me to expand to the 2400 target? After all of it, the number at the centre of everything still sits there, exact and unexplained, waiting for someone to say why. 299,792,458 meters every second. Around 186,000 miles in the time it takes to say the word. We know it to 9 significant figures. We have known it exactly since 1983, when the world stopped measuring the speed of light and started using it to define the meter itself. The number no longer answers to a ruler, the ruler answers to it, and still, no one can tell you why it is that number. You can climb through every layer of physics we have and never find the reason. Relativity does not derive the speed of light. It assumes it. It takes the constancy of that speed as a given, a postulate laid down at the start, and builds 100 years of confirmed prediction on top of it. Special relativity explains why the speed is the same for every observer. It explains why nothing with mass can reach it. It cannot explain why the universe chose this value and not some other. The number is a fact without a father. Sit with that for a moment. We can build a 17-mile ring of superconducting magnets and push protons to within 1/1000th of light speed. We can watch galaxies recede faster than any beam could chase them, carried apart by expanding space. We can measure a possible photon mass and find it smaller than 1/1000th of a billionth of a billionth of a billionth of a billionth of a kilogram, so small it might as well be zero. We can do all of that. And when a child asks why the limit is set exactly where it is, the honest answer is that we do not know. But here is the truth that matters more than the number. The limit was never really about light. Light is simply the fastest thing that obeys it. The rule underneath is quieter and far stranger. No cause can outrun its own effect. That is the real law. A signal, a push, a piece of news, an influence of any kind cannot arrive anywhere before the moment it was sent. If anything could, there would be reference frames, perfectly valid ones, in which the effect came first and the cause came after. Reality would stop making sense. The order of before and after would dissolve. So the speed of light is the speed of cause and effect. It is the pace at which the universe is allowed to change its own mind. Every event you have ever lived sits inside a cone of possibility, a boundary expanding outward at exactly that speed, marking everywhere your influence can ever reach and everywhere that could ever have reached you. Everything outside it is sealed away, not hidden, not too far for now, simply, permanently, beyond touch. And that same boundary is what holds the world together. Notice the shape of it, the very limit that seals off the stars, that keeps the light of vanished galaxies drifting toward us for billions of years, that guarantees you can never visit most of what you can see is the same limit that keeps reality coherent. The wall that isolates is the wall that protects. Loosen it, let one signal slip past, and you do not get faster travel. You get a universe where effects precede causes, where the past is no longer safe, where the thread that ties one moment to the next comes undone. The barrier is not cruelty, it is structure. It is the reason there is an order to things at all, the reason your yesterday stays yesterday and your tomorrow waits its turn. So the two feelings you have been carrying belong together. The loneliness of it, the vast silent distances that light takes minutes and centuries and eons to cross, and the comfort of it, the fact that anything holds it all. They are the same fact seen from two sides. The universe is enormous and mostly out of reach precisely because it is governed. Precisely because a rule holds everywhere without exception, in every accelerator, across every void, at the edge of every horizon. Physicists have thrown everything at that rule. The whole collaboration once thought it had beaten light and found a loose cable. Jets of matter seem to fly across the sky at 10 times the limit and turn out to be an illusion of angle and timing. Warp geometries and hypothetical particles circle the edges of what might be possible, still bound, in the end, by walls of energy no one can pay. The rule has survived every real test. It has never once broken. And so we are left where we began, holding a number we can measure to perfection and cannot explain at all. 299,792,458. Exact. Unexplained. The most reliable fact in all of science, and one of its deepest mysteries, sharing a single line of digits. Let the strangeness settle now, gently, without any dread in it. There is nothing here to fear, only a quiet wall standing at the outer edge of everything, older than the stars, patient as the dark, keeping the story of the universe readable from one moment to the next. The distance it enforces is the same distance that lets things be. You do not need to solve it tonight. No one has solved it yet. You can simply let it be true, the way it has always been true while you rest. The light from the sun that reached you today left it more than 8 minutes ago. The starlight above you is older still. All of it arrived exactly on time, at the only speed the universe allows. Sleep well tonight. Good night.